Welcome back, everyone. Today, we're taking a pretty fascinating journey through what you could almost call the biological life cycle of a C++ object. Because, just like us, every single object in C++ has a birth, it has a period of self-awareness where it does its actual work, maybe even a phase where it clones itself, and ultimately, a death. And if you've got an upcoming computer science exam, or maybe a really tricky programming assignment, understanding this entire life cycle, from creation all the way to memory cleanup, is absolutely essential. By the end of this explainer, you are going to have a rock-solid grasp of exactly how objects come to life and how they gracefully exit your programs.
Okay, let's dive into this. Here is our roadmap for today. We'll be covering constructors, the this pointer, copy constructors, destructors, and then we'll wrap up with a final exercise.
Section 1. Constructors, or the birth and initialization of objects.
Let's start right at the very beginning. Every object needs a starting point, right? A moment where it basically springs into existence and gets ready to action. Well, in the world of C++, this critical moment of birth is handled by a special function called a constructor. To put it formally, a constructor is a member function of a class, which initializes objects of that class. But really, its primary, absolute, most vital role is just to set up the initial state of the data members the exact moment that object is created in memory. Think of it kind of like setting the factory defaults on a brand new smartphone before you even take it out of the box.
Now, if you want to ace your assignments, you literally need to memorize these unbreakable rules of constructors. I mean it. The compiler is totally unforgiving if you mess these up. First up, a constructor must have the exact same name as the class itself. Second, it's got to be a public member. I mean, think about it. Otherwise, you wouldn't even be able to create an object from outside the class. Third, absolutely no return values. None. Not even void. And finally, if you just completely forget to write one, don't panic, C++ has your back. The compiler will automatically generate a default constructor for you with an empty body, purely so the object can exist.
Let's act as a code translator for a second. Looking at this perfectly simple example, notice how our class is named car. And then inside, directly under the public access specifier, we have our constructor, which is also simply named car double parentheses. There's no int, there's no void, literally nothing before the word car. This perfect name match is exactly what the compiler is looking for to actually bring your object to life.
And this brilliantly illustrates the generic blueprint you should really just lock into your head. You've got your class name, your access specifiers, and then nestled safely right there in the public section is the constructor code. It just sits right alongside your other variables and functions, waiting to be called the very second an object is instantiated.
Section 2. The this pointer, or object self-awareness.
So now that we've successfully brought our object into the world, we hit a kind of interesting philosophical programming question. How does the object actually know who it is? When it's doing work, how does it refer to itself? Well, every object in C++ has access to its own address through an implicit pointer called this. The this pointer is a reference variable that points directly to the current object's state and behavior. It's passed secretly, right behind the scenes, as an argument to all non-static member functions. Basically, it gives the object a way to say, hey, I'm talking about my variables right now.
There are really two main reasons we explicitly write out the this pointer in our actual code. One is to return a reference to the calling object. But that first point right there, that is where I really want you to focus today. Because it is a classic common mistake, and instructors absolutely love putting this exact trap on exams. And that is using this when a local variable's name is the exact same as a member variable's name.
Let's put these two snippets side by side. Imagine a class with a member variable x and a constructor that takes a parameter, also named x. If you just write x equals x, the compiler gets completely lost. It just assumes you are assigning the local parameter to itself and completely ignores the object's actual member variable. The result? Your object's data stays uninitialized and probably outputs a 0. But if you use the pointer and write this.x equals x, the compiler knows exactly what's up. You are clearly saying, take the local variable x and assign it to this object's member variable x. And boom, the output perfectly matches your intention, 10.
Now, what's really interesting about seeing this in the wild is how clean it looks. Check out lines 11 and 12 here. We have a function argument x and a private data member also named x up on line 8. By just using this:x equals x, we totally resolve that naming conflict. The left side explicitly points to the object's memory, and the right side uses the passed-in argument. Seriously, keep this syntax in your toolkit. It is going to save you hours of debugging.
Moving right along. Section 3. Copy constructors, or cloning objects.
So sometimes, instead of starting totally from scratch, we want to create a brand new object by duplicating one that's already been born and initialized. This is where copy constructors come in, and you need to draw a hard line between the two types here. If you don't write one yourself, the C++ compiler graciously creates a default copy constructor for you. But beware, this default version only does what's called shallow copying. That means it just copies the raw memory addresses. If you have complex data like dynamic memory, yeah, things are going to break. To safely clone complex objects, you absolutely need a user-defined copy constructor that performs deep copying, ensuring every single piece of data gets its own brand new isolated spot in memory.
Section 4, Destructors, the end of the lifecycle. And now, we reach the final stage. All good things must come to an end, and in programming, leaving old objects lying around causes massive memory leaks. So, we need a way to clean up. The syntax for a destructor is incredibly straightforward, but very specific. Just like a constructor, it shares the exact name of the class, and it has no return type. The key differentiator, though, the thing that literally tells the compiler, hey, this is the end, is the tilde symbol, that little squiggly line right before the class name. For example, Sue, my class.
You don't usually call destructors yourself, the system does it for you. But for your upcoming tests, I highly advise you to memorize these 4 exact triggers that cause a destructor to be called automatically. 1. When the function containing the object ends. 2. When the entire program terminates. 3. When a specific block of code containing local variables finishes executing. And 4. Dynamically, whenever the delete operator is explicitly called by the programmer. When any of these 4 things happen, the object goes out of scope, the destructor fires, and the memory is wiped clean.
Section 5, Final Recap and Exercise.
All right, that brings us to our final section. We've watched our object be born, become self-aware, clone itself, and safely deconstruct. Let's do a rapid-fire recap to really solidify your retention here. The crucial point is this core set of rules. Constructors bring objects to life by initializing them. They must be public, and they must share the class name. The this pointer gives the object its own address, which brilliantly prevents variable shadowing bugs. Copy constructors are for cloning, and you definitely must remember the difference between the compiler's shallow copy and your custom deep copy. Finally, destructors use a tilde and automatically clean up memory when an object goes out of scope.
Okay, now it's time to put all of this into practice with the Piggy Bank Challenge. Here is your assignment. I want you to create a class called addAmount with a data member initialized to $50. Then, write 2 constructors. The first takes no parameters and adds nothing to the bank. The second takes an amount as a parameter and adds it to the existing $50. Think about how you'll name your variables and whether you're going to need that this pointer. Go ahead and pause the explainer right now, open up your compiler, create an object, and see if you can display the final amount. Good luck, keep coding, and I will see you in the next explainer.